Imagine standing on the lunar surface as the sun begins its slow descent toward the horizon. Earth hangs above you, brilliant and blue, a fragile ornament suspended in velvet darkness. The shadows lengthen across ancient craters. The light takes on a quality unlike anything experienced on our world, sharp, unfiltered, almost crystalline in its purity. You watch as the sun touches the jagged peaks in the distance, and in that moment, you realize something profound. When darkness falls here, it will not lift for 14 Earth days. 2 full weeks of night. 2 weeks where no photon of sunlight will reach this desolate plain. 2 weeks of cold so absolute, it transforms the landscape itself. This is the hidden reality of lunar exploration, the silent killer that waits patiently above us. It is not radiation, though that presents its own dangers. It is not meteorites, though they strike without warning or atmosphere to slow them. The greatest threat to permanent human presence on the moon is something far more fundamental. Darkness. Simple, patient, merciless darkness. Humanity stands once again on the threshold of the moon. NASA's Artemis program promises to return astronauts to the lunar surface within years. Plans for permanent bases are being drawn. Private companies speak of lunar tourism, of hotels with Earth views, of mining operations that could fuel an entire off-world economy. The enthusiasm is intoxicating. The vision is grand. Yet beneath all these dreams lies a challenge we have never truly faced. We have walked on the moon. We have driven rovers across its plains. We have planted flags and collected samples. But we have never survived a lunar night. Every Apollo mission was carefully timed to land during lunar dawn, ensuring astronauts had roughly 1 Earth week of continuous daylight before departure. They left before the sun set. They departed before darkness could reveal its true nature. The equipment left behind, flags, retroreflectors, scientific instruments, faced the night alone. Much of it failed, not from age, but from the temperature extremes that darkness brings, cycles so violent they fracture metal and shatter seals designed to last decades. The moon rotates so slowly that its day-night cycle stretches across 29.5 Earth days. Approximately 2 weeks of brilliant, unrelenting sunlight where surface temperatures soar past 250 degrees Fahrenheit. Then 2 weeks of darkness where temperatures plunge to minus 280 degrees Fahrenheit, colder than anything naturally occurring on Earth, colder than liquid oxygen. This is not merely an inconvenience, it is a fundamental barrier to everything we hope to accomplish. In the silence of that long night, solar panels become useless artifacts. Batteries designed for Earth's gentle 24-hour rhythm drain within hours. Machinery contracts, seals fail, lubricants freeze solid. The moon does not simply get cold. It becomes hostile in ways that challenge the very foundations of our engineering knowledge. Every material we use, every power system we design, every habitat we construct must somehow endure this cycle indefinitely, without failure, without the resupply missions we take for granted on the International Space Station. Tonight, we will journey into this darkness together. We will explore why 14 days without sunlight presents challenges that dwarf those of reaching the moon in the first place. We will discover the hidden physics of cold, the strange behavior of materials at extreme temperatures, and the ingenious solutions engineers are developing to keep humanity alive when the sun abandons the lunar horizon. We will ask not just how we survive, but what surviving truly means in an environment so alien that our instincts, honed over millions of years on Earth, offer no guidance whatsoever. Before we descend into that waiting dark, I invite you to ground yourself in this moment. Leave a comment below. Tell us where you are watching from and what time it is in your world right now. As we explore the eternal night of the moon, it helps to remember we are all still orbiting together beneath the same sun. Now, let us begin our descent into the silent darkness waiting above us. Before we can comprehend the challenges of lunar survival, we must first understand something fundamental about the moon, something so different from our experience on Earth that it reshapes every assumption we hold about day and night. Time on the moon does not tick as it does here. A single day unfolds not in the familiar rhythm of 24 hours, but across the span of nearly an entire month. One lunar day, one complete cycle from sunrise to sunrise, lasts approximately 29.5 Earth days. This is not simply a matter of different clocks or altered schedules. This is a transformation of the most basic pattern that governs life as we know it. On Earth, we wake with the sun and rest in darkness, cycling through light and shadow in a dance that has remained constant for billions of years. Our bodies, our minds, even the structure of our cells are built around this rhythm. But on the moon, the sun rises slowly, almost imperceptibly, creeping above the horizon over the course of hours. Then it hangs in the black sky, unmoving for what would be days on Earth, casting hard shadows across the grey landscape. There are no clouds to soften its light, no atmosphere to scatter its rays into gentle dawn or dusk. The transition from day to night is not a gradual fade, but an abrupt plunge from brilliance into absolute void. The reason for this strange temporal rhythm lies in a phenomenon called tidal locking, an elegant gravitational dance between Earth and its closest companion. The moon rotates on its axis at precisely the same rate that it orbits Earth. One rotation takes the same time as one orbit, approximately 27.3 days. This synchronization is not coincidence, but the result of billions of years of gravitational influence. Long ago, when the moon was younger and its rotation faster, Earth's gravity tugged unevenly on the lunar surface, creating tidal bulges that gradually slowed the moon's spin until the same face permanently pointed toward Earth. We see this locked face every night when we look up at the moon. The far side, often incorrectly called the dark side, remains hidden from our view, though it receives just as much sunlight over the course of a lunar day. This tidal locking creates the moon's peculiar day-night cycle. As the moon orbits Earth, different portions of its surface gradually rotate into and out of sunlight. The result is a slow, methodical progression. Approximately 14 Earth days of continuous, unrelenting sunlight, followed by 14 Earth days of complete, unbroken darkness. There is no respite, no brief nights to cool the scorching surface during the day, no fleeting dawns to warm the frozen terrain during the night. The moon experiences extremes in their purest form, stretched across weeks rather than hours. To truly grasp what this means, imagine standing on the lunar surface as the sun begins to rise. You would have time to eat breakfast, watch the entire event unfold over several Earth days, and the sun would still be climbing toward its zenith. Once overhead, it would track slowly across the sky at a pace barely perceptible to human observation. You could set up a solar panel, go to sleep for 8 hours, wake up, and the sun would have moved only about 12 degrees, roughly the width of your hand held at arm's length. Day after day, the sun would continue its journey, heating the surface to temperatures that would boil water, melt lead, and cook any unprotected equipment or human tissue within minutes. Then, as the sun finally approaches the horizon after 2 full weeks, darkness comes. Not the soft darkness of an Earth evening, where city lights glow and the atmosphere still scatters some twilight. On the moon, when the sun sets, it is as if someone has switched off the universe. The temperature begins to plummet immediately, dropping hundreds of degrees within hours. The stars emerge with a clarity and brilliance impossible to see from Earth, undimmed by any atmosphere, unchanging and cold. And this darkness persists. One day passes, then two, then a week, then 2 weeks. The lunar night is not a pause in the day, it is an epoch unto itself. Earth's rapid day-night cycle is one of the primary reasons life flourished here. The rotation of our planet every 24 hours creates a dynamic environment where temperatures moderate, where photosynthesis can occur during the day and respiration continues through the night, where organisms can adapt to predictable patterns of light and dark. This rhythm became embedded in nearly every form of life on Earth, from the circadian clocks in human cells to the opening and closing of flowers, from the hunting patterns of nocturnal animals to the migration cycles of birds. Life on Earth did not merely exist alongside the 24-hour day. It evolved because of it, shaped by its constancy, optimized for its rhythm. The moon offers no such pattern. Its extremes are vast, prolonged, and unforgiving. When humanity first ventured to the moon, this strange temporal reality shaped every decision. The Apollo missions, those brief, historic moments when human feet touched another world, were meticulously planned around the lunar day. Every landing occurred during lunar morning, when the sun had just risen and would remain in the sky for the duration of the mission. This timing was not accidental, it was essential. Arriving during lunar morning meant the astronauts would have maximum daylight for their exploration, their experiments, and most crucially, for their solar panels and thermal systems to function. Landing at lunar noon would have subjected them to the most extreme heat. Landing at lunar dusk would have risked being caught in the onset of the 2-week night, a scenario for which the Apollo landers were not designed to survive. The longest any human has ever remained on the moon is approximately 75 hours, just over 3 Earth days. This record was set by the crew of Apollo 17 in December 1972, the final manned mission to the lunar surface. Eugene Cernan and Harrison Schmitt spent that time conducting geological surveys, collecting samples, and marveling at the barren beauty surrounding them. But even during those 75 hours, they were acutely aware of time. They knew the sun would continue its slow march across the sky. They knew their window was limited. They knew that the lunar night was always approaching, patient and inevitable. 75 hours is less than 1/10 of a full lunar day. In that time, the astronauts experienced only a fraction of the moon's cycle. They never witnessed a lunar sunset. They never felt the creeping cold of the approaching night. They departed before the darkness arrived, returning to Earth while the sun still hung in the sky above their landing site. The lunar night remained, as it does even now, an experience reserved for robotic landers and future explorers, a realm humans have seen only in data and imagination. Understanding lunar time is not merely an academic exercise. It is the foundation upon which all plans for lunar survival must be built. When we speak of living on the moon, of establishing habitats, of creating sustainable outposts, we are speaking of adapting to a world where time itself operates on a scale alien to human experience. We must design systems that can function for 2 weeks without sunlight. We must create habitats that can endure temperature swings spanning hundreds of degrees. We must prepare human minds and bodies for isolation in darkness that lasts longer than most vacations, longer than most illnesses, longer than the time it takes for seasons to change on Earth. The moon does not bend to our rhythms. It does not accommodate our expectations. Its day unfolds with the slow inevitability of geological time, indifferent to human presence, untouched by our need for familiarity. To survive, there is to surrender our terrestrial assumptions and embrace a new understanding of what a day can be. Not a fleeting passage of hours, but a vast stretching of time, measured not in sunrises and sunsets, but in the slow turning of a world locked in an ancient gravitational embrace. And so, as we stand on the edge of returning to the moon, not just to visit but to stay, we must reckon with this first and most fundamental challenge. The lunar day is not our enemy, but neither is it our ally. It simply is, a fact of celestial mechanics, a rhythm written into the fabric of the Earth-Moon system billions of years ago. To live on the moon is to learn its time, to respect its cycles, and to build our survival around a truth that cannot be negotiated. The night will come. It will last 2 weeks, and everything we create must be prepared to endure it. As we contemplate our journey to the moon, we encounter a paradox that defines the lunar environment more than any other characteristic. The moon is simultaneously an oven and a freezer, a world where temperature swings are so extreme they challenge the very foundations of matter itself. To survive the lunar night, we must first understand the thermal nightmare that governs every moment on this airless world. During the lunar day, when the sun climbs slowly above the horizon and begins its 2-week arc across the black sky, the surface heats relentlessly. Without an atmosphere to scatter or absorb the solar radiation, every photon that strikes the regolith transfers its energy directly into the ground. Temperatures rise steadily, climbing past the freezing point, past comfortable room temperature, past the heat of a summer day. They continue upward, surpassing the boiling point of water at sea level on Earth, reaching peaks of 127 degrees Celsius, approximately 260 degrees Fahrenheit. This is not just uncomfortable heat. This is metal warping, rubber melting intensity that transforms the lunar surface into a realm where materials behave differently than they do in earthly laboratories. To stand on the moon during high noon, properly shielded of course, would be to experience heat radiating from beneath your feet with an intensity that few places on Earth can match. The darkest volcanic rocks absorb this energy hungrily, becoming hot enough to burn through certain materials within moments of contact. Equipment left exposed must be designed not merely to function in heat, but to endure it, cycle after cycle, without degradation. Then the sun sets, and everything changes. As the 2-week day gives way to the 2-week night, the absence of atmosphere reveals its most profound consequence. On Earth, our blanket of air acts as both insulator and distributor. Heat absorbed during the day is trapped, circulated, and slowly released throughout the night. Temperature drops are gradual, moderated by oceanic currents, atmospheric winds, and the thermal mass of the environment itself. But the moon has no such buffer. The moment sunlight ceases to strike the surface, heat begins to radiate directly into space. There is no air to hold it back, no clouds to reflect it downward, no wind to carry warmth from one location to another. The temperature plummets with startling speed. Within hours, the furnace becomes a deep freeze. The thermometer drops past comfortable temperatures, past the freezing point of water, past the coldest winters recorded in Antarctica. It continues falling, reaching depths of negative 173 degrees Celsius, approximately negative 280 degrees Fahrenheit. This is colder than liquid oxygen, colder than the surface of Mars at its polar caps, colder than anywhere that exists naturally on the surface of Earth. The total temperature swing, from the peak of day to the depths of night, exceeds 300 degrees Celsius. To put this in perspective, imagine designing a structure that must function flawlessly, whether it is hotter than boiling water or colder than liquid nitrogen, and must transition between these extremes repeatedly, predictably, eternally. Metals expand in heat and contract in cold. Seals that remain flexible at high temperatures become brittle and crack when frozen. Electronics that operate reliably in moderate conditions can fail catastrophically when subjected to such punishment. Glass, composites, ceramics, each material responds differently to thermal stress, and each junction between dissimilar materials becomes a potential point of failure. Human biology operates within a thermal envelope so narrow it seems almost absurd when compared to the lunar extremes. Our core body temperature hovers around 37 degrees Celsius, roughly 98.6 degrees Fahrenheit. Deviation by even a few degrees in either direction causes distress. A rise to 40 degrees Celsius brings fever and confusion. A drop to 35 degrees Celsius initiates hypothermia. Our existence is balanced on a knife's edge, dependent on maintaining precise conditions within a range of perhaps 10 degrees. Yet we propose to inhabit a world where the environment swings across 300 degrees with the regularity of a pendulum. This is not a challenge to be solved with a simple heater or air conditioner. This is a fundamental confrontation with thermodynamics. Every habitat on the moon must be a fortress against temperature, insulated with materials that can withstand not just heat or cold, but the constant cycling between them. Every seal must remain intact as materials expand and contract. Every surface exposed to the environment must be engineered to endure thermal stress that would shatter conventional construction within days. The moon's lack of atmosphere is both the cause and the cruel amplifier of this temperature nightmare. Without air molecules to carry heat through convection, energy transfer happens primarily through radiation and conduction. Touch the wrong surface during lunar day, and heat floods into your suit through direct contact. Step into shadow during lunar night, and your own body heat radiates away into the infinite cold of space, barely slowed by the vacuum around you. It is instructive to consider Mars, humanity's other primary target for exploration. Mars possesses an atmosphere, thin as gossamer compared to Earth's, composed mostly of carbon dioxide, and providing barely 1% of the pressure we experience at sea level. Yet even this whisper-thin veil makes a profound difference. Martian temperatures still swing dramatically between day and night, but the extremes are moderated. Daytime highs near the equator might reach 20 degrees Celsius, while nighttime lows drop to perhaps negative 70 degrees. This is still harsh, still challenging, but the swing is less than half of what the moon experiences. That fragile atmosphere, barely substantial enough to create wind, provides just enough thermal buffer to make Mars seem almost hospitable by comparison. The lunar temperature nightmare is not simply an engineering obstacle. It is a constant, unforgiving force that shapes every decision, influences every design, and demands respect from anyone who dares to venture there. Materials that seem robust on Earth become fragile. Systems that appear redundant become necessary. The margin for error shrinks to almost nothing. As we contemplate survival through the lunar night, we must remember that darkness is only part of the challenge. Cold is the other half of the equation. Cold so profound it transforms the familiar into the alien, where substances change their fundamental properties and where the warmth of life must be guarded with the vigilance usually reserved for precious flame in an endless winter. The temperature extremes of the moon are not merely numbers on a thermometer. They are a fundamental test of our understanding of physics, engineering, and the delicate balance required to keep humanity alive in a place where nature offers no compromise, no middle ground, only extremes that stretch from one edge of survivability to the other. In the profound silence of the lunar night, before the temperature plunges and before the dust settles into its frozen dance, there is a moment when everything simply stops. Not gradually, not with warning systems blaring, but with the quiet finality of a candle flame extinguished by an unseen hand. This is the moment when the sun dips below the lunar horizon and every solar panel, every photovoltaic cell, every energy-harvesting surface becomes nothing more than an expensive piece of inert metal and silicon. The power dies, and with it, so does nearly everything else. Solar power is not just a convenient energy source for lunar exploration. It is the foundation upon which almost every mission ever sent to the moon has been built. From the earliest Soviet landers to the Chinese rovers that have traversed the far side, solar panels have been the default, the obvious choice, the technology we understand so well that it seems almost foolish to question their use. They are lightweight, reliable, efficient, and require no fuel to be transported across the void of space. Under the brilliant, unfiltered sunlight of the lunar day, they perform magnificently, converting photons into electricity with elegant simplicity. But the moon does not offer continuous daylight, and here, in this simple astronomical fact, lies one of the most profound engineering challenges humanity has ever faced. The mathematics of lunar night are unforgiving. When the sun sets on the moon, it does not return for 336 hours, 14 Earth days, 2 full weeks of absolute darkness. No twilight to ease the transition, no atmospheric scattering to provide ambient light. Just darkness, complete and total, stretching across the desolate plains and the crater-scarred highlands. For those 336 hours, a lunar habitat or rover must survive entirely on stored energy. Every watt needed for heating, every joule required for communication with Earth, every electron necessary to keep computers from freezing into useless blocks of silicon must come from batteries charged during the previous day. This is not a small engineering problem. This is not a matter of simply adding more battery capacity. The energy requirements during lunar night are staggering. Heaters must run continuously to prevent equipment from dropping to temperatures that would shatter metal and freeze lubricant solid. Life support systems, if humans are present, cannot pause for 2 weeks. Communication arrays must maintain contact with Earth, transmitting signals across 240,000 miles of space. Scientific instruments must be kept warm enough to function when the sun returns. The power demand does not decrease during the night. In many ways, it increases. Current battery technology, as advanced as it has become, cannot bridge this gap, not practically, not economically. Lithium-ion batteries, the workhorses of modern space exploration, have impressive energy density for terrestrial applications, but to store enough power for 336 hours of continuous operation on the moon would require batteries so massive, so heavy, that launching them would cost more than entire missions. Every kilogram sent to the moon carries a price tag measured in tens of thousands of dollars. A battery system capable of sustaining a modest lunar habitat through one night could weigh several tons, and those batteries would need to be recharged during the following day, which means even more solar panels, which means even more weight, spiraling into an equation that simply does not balance. The lunar surface is littered with the consequences of this imbalance. China's Chang'e 3 lander and its Yutu rover which touched down in 2013, were designed to survive multiple lunar nights through a combination of radioisotope heater units and careful power management. U-2 survived its first night, but experienced malfunctions that eventually left it immobile. The Chang'e 4 mission, which landed on the far side of the Moon, has fared better, with both lander and rover surviving multiple nights through meticulously engineered thermal control and power systems. But these are not triumphs of abundance. They are victories of survival, achieved by shutting down nearly everything non-essential and hoping that critical systems can be revived when dawn returns. Private missions have faced even harsher realities. Israel's Bereshit lander crashed in 2019 before it could face a lunar night, but its design acknowledged the challenge. Surviving even one night would have required technology the small spacecraft simply could not carry. India's Vikram lander, part of the Chandrayaan-2 mission, lost contact during its descent in 2019. But even had it landed successfully, it was designed to operate for only one lunar day, a mere 14 Earth days. The night was considered insurmountable. Japan's ISpace Mission 1 lander crashed in 2023, and again, its operational timeline was measured in hours of daylight, not cycles of day and night. These are not failures of engineering competence. They are acknowledgements of physical reality. The lunar night is not simply a period of inconvenience. It is a deadline, a hard limit beyond which most current technology cannot persist. And this creates a cascading failure effect that transforms a power problem into an existential crisis. When solar panels go dark, batteries begin to drain. When batteries drain, heaters shut down. When heaters shut down, temperatures plummet. When temperatures plummet, electronics fail. When electronics fail, communication ceases. When communication ceases, the mission is over. Each system depends on the one before it, and all of them depend on power that, for 336 hours, simply is not there. Some missions have attempted hybrid approaches. Small radioisotope heating units provide warmth without electricity, using the natural decay of plutonium to generate heat. But these are not power sources in the traditional sense. They cannot charge batteries or run equipment. They merely slow the descent into frozen silence. Solar rechargeable systems combined with advanced thermal insulation can extend survival, but extension is not the same as thriving. A habitat that merely survives the night is not a permanent presence. It is a temporary visitor, counting hours until either sunrise or system failure, whichever comes first. The Moon demands more from us. It demands solutions that transcend the limitations of daylight. As we contemplate permanent human presence on the lunar surface, as we design habitats meant to last years rather than days, we must confront this fundamental truth. Solar panels, for all their elegance and efficiency, are creatures of light, and the Moon, for half of every month, is a realm of darkness. What thrives in sunlight may not survive the night, and what cannot survive the night cannot call the Moon home. When the last rays of sunlight slip beyond the lunar horizon, solar panels fall utterly silent. No twilight, no afterglow. Just a switch flipped by the cosmos itself. For 14 Earth days, the Moon turns its cold face toward the universe, and any outpost that relies only on starlight and batteries begins a slow, inevitable countdown toward darkness. To survive this long night, we turn to a power source older than stars themselves, the energy locked inside atoms. Nuclear power on the Moon is not just an engineering choice. It is a philosophical one, a decision to bring one of humanity's most potent and most controversial technologies into the pristine silence of another world. Long before we dreamed of lunar bases, we tested this idea in the deep vacuum between planets. In the outer solar system, sunlight becomes a weak and distant memory. Solar panels that thrive in Earth orbit grow useless beyond the orbit of Jupiter. Yet our spacecraft still whisper to us from billions of miles away. They do so because of a quiet, steady heart beating inside them. The radioisotope thermoelectric generator, or RTG. An RTG does not split atoms like a reactor. It does something simpler and in some ways more elegant. It takes advantage of nature's slow clock. Certain radioactive materials, like plutonium-238, decay over time, releasing heat in a steady, predictable rhythm. This heat flows through special materials called thermocouples, which convert temperature differences directly into electricity. No moving parts, no turbines, just a solid block of material slowly cooling as it powers instruments, heaters, and radios. This simplicity is its strength. There are no belts to break, no oil to leak, no sunlight required. As long as the radioisotope continues to decay, the electricity flows. The power gently diminishes over decades, but it doesn't flicker with passing shadows or storms. It is as close as we have come to a mechanical heartbeat that can last a human lifetime in space. The Voyager probes are the most famous proof. Launched in 1977, they rode gravity past the giant planets and kept going beyond the orbit of Neptune into the thin edge of interstellar space. Their RTGs have been cooling for nearly half a century, and yet, even now, their instruments still wake, take measurements, and send home faint signals that cross the void for more than a day before reaching Earth. These messages are powered not by the sun, but by atoms slowly reshaping themselves in silent darkness. To imagine that same kind of power on the Moon is to imagine a lunar base that does not fear sunset. An RTG buried in the regolith could provide a gentle, continuous trickle of energy to keep instruments warm, electronics alive, and a core of life support systems quietly running. For small outposts or robots, that might be enough. A single reliable ember glowing through every night. But a human settlement is hungrier. It needs more than embers. It needs a hearth. This is where another idea steps onto the stage. Small, modular nuclear reactors. Unlike RTGs, these are true reactors, designed to split atoms in a controlled chain reaction, releasing far more energy from much less fuel. For the Moon, one of the leading concepts is NASA's Kilopower project. Kilopower imagines a compact reactor, only a few meters tall, with a solid core of uranium and a set of heat pipes drawing away the energy of fission. That heat is then turned into electricity by efficient converters, supplying tens of kilowatts of power, enough to run habitats, laboratories, life support, and even heavy machinery. Multiple units could work together, like a small forest of artificial suns, each quietly burning in metallic silence. What makes such reactors particularly tempting for the lunar night is their independence from the lunar day. They do not care whether the surface is drenched in sunlight or plunged into shadow. Their power curve is a flat line, unwavering, not just over days, but over years. In a realm where 14 days of darkness can be fatal, that kind of consistency is not just convenient, it is transformative. And there is another advantage, one that becomes especially precious in the deep freeze of lunar night. Nuclear systems do not only generate electricity, they also generate heat as a so-called waste product. On Earth, heat is often something to be dissipated, managed, thrown away into the air or sea. On the Moon, heat is life. The same warmth that would be vented from a reactor's radiators can be routed into habitats, into greenhouses, into storage bays where fuel, lubricants and vital fluids would otherwise freeze solid. Pipes carrying reactor heat could snake beneath floors and along walls, turning structures from fragile shells into islands of stability. Even RTGs, with their lower power, can double as both battery and furnace, hugging rovers and instruments with a thermal blanket that shields them from the brutal cold. Yet for all these promises, nuclear power in space carries a shadow that is not physical, but human. To launch nuclear material from Earth is to ask difficult questions about safety, about trust, about risk that stretches far beyond any single mission. Before a reactor or RTG reaches the Moon, it must pass through the most delicate environment we know, our own planet's atmosphere. Space agencies design these systems to survive accidents. The fuel forms are hardened, cased, and tested under extreme conditions. They are meant to remain intact in the worst scenarios imagined. So far, the record of nuclear launches has been largely safe, and missions that used RTGs from Voyager to Curiosity have flown without incident. Still, the worry lingers. What if a rocket fails on ascent? What if fragments fall back through the sky? Even if the probabilities are low, they are not zero, and for many, that is enough to stir anxiety. For others, the idea of spreading nuclear technology beyond Earth raises more philosophical concerns. Should we carry such concentrated power into the quiet landscapes of the Moon or Mars? What responsibilities accompany that act? Ethical debates emerge not only around accidents, but around legacy. A reactor on the Moon might power a habitat for decades, but long after we leave, if we ever do, its remains will sit in the ancient dust. Some argue this is a small footprint compared to the potential knowledge and survival it enables. Others ask whether we should treat other worlds as simply blank canvases for our most powerful machines. Public perception follows these currents closely. For some, nuclear evokes images of bombs, waste, and disasters. For others, it represents a dense, efficient, and controllable source of energy that could free exploration from the fragile leash of sunlight. Both intuitions carry truths and fears shaped by history on Earth, from power plants to treaties. In the calm silence of the lunar night, the atoms themselves remain indifferent to these arguments. Plutonium will decay whether we use its heat or not. Uranium will sit in rock until someone decides to wake it. The decision is ours, whether to accept the risks and responsibilities of nuclear power as the price of a permanent presence beyond Earth, or to search for other ways to endure the darkness. If we do choose nuclear solutions, the Moon may become the first place where civilization rests, not on a star's daily rise and fall, but on a man-made, continuous glow. A world where night is no longer a threat, but a backdrop, against which a small, steady core of atom-born warmth holds out, waiting patiently for the sun to return. The Moon does not simply turn its back on the sun. It turns its full attention to the cold. On Earth, materials live gentle lives. Steel bridges flex with the seasons. Rubber tires harden in winter and soften in summer. Plastic casings warm in the sun and cool at night. The changes are gradual, cushioned by air, clouds, and weather that, for all their violence, move in relatively narrow bands of temperature. On the Moon, there is no such mercy. When lunar day gives way to night, the surface does not cool, it crashes. Temperatures fall hundreds of degrees over the course of a single airless dusk. Metal, rock, glass, everything is plunged into a deep, unbuffered cold. Then, 2 weeks later, the sun returns, and the same materials are suddenly thrust back toward boiling heat. Every lunar day is a breath of fire. Every lunar night is a collapse into glass. Engineers have a name for this repeated stress: thermal cycling fatigue. It is less a single catastrophic event than a quiet counting of failures. Each time the sun rises, metal expands, pushing against bolts, joints, and welds with invisible force. Each time the sun sets, that same metal contracts, pulling away, shrinking, straining against the very fasteners meant to hold it in place. Over dozens, then hundreds of cycles, these microscopic stretches and squeezes carve tiny cracks into the material. Given enough time, those hairline fractures can become fault lines. On Earth, we design around this. Bridges have expansion joints, buildings sway, airplanes flex and bend in flight. But they do so within a relatively gentle thermal envelope. The moon replaces that envelope with a hammer. In this relentless alternation between furnace and freezer, metals begin to change personality. At room temperature, many alloys are tough, forgiving, capable of bending and absorbing force before they break. Under extreme cold, that same metal can suddenly become brittle, like a pane of glass pressed too hard at one edge. A familiar tragedy offers an echo of this transformation, the sinking of the Titanic. Early 20th century steel, immersed in freezing Atlantic waters, behaved differently than its builders expected. Analyses performed decades later suggested that the steel's toughness dropped sharply in the cold, making it more prone to fracture when struck by the iceberg. Metal that seemed strong in normal conditions became, in that night's sea, more like a fragile shell. Place that same concept on the moon, where temperatures fall far below anything the Titanic ever met, and the risk become more than historical. A structural beam, a pressure vessel, a landing leg, designed for strength at human-friendly temperatures, may stiffen and lose ductility in lunar night. Under a sudden load, an impact, or even accumulated strain from repeated thermal cycling, it might not bend and deform, it might snap. And metal is only the beginning. Consider the softer, more vulnerable materials that quietly hold life support systems together. Rubber seals that keep air from leaking, plastic housings that insulate wires, lubricants that let gears move, hinges swing, pumps turn. On Earth, we barely think about them. They are background actors, performing reliably in the familiar script of 20 degrees Celsius rooms and modest winter mornings. In deep cold, that script is rewritten. Rubber, which is elastic and springy at ordinary temperatures, can stiffen until it behaves more like hard plastic. Seals that once flexed to fill microscopic gaps can shrink and crack, leaving tiny paths for precious air to escape. A thin line around a hatch, a valve, or a viewing port becomes the difference between pressure and vacuum. Plastics, too, change. Some contract more than the metals they are attached to, tugging on screws and clips, pulling away from mounting points, splintering under stress. Others turn brittle, fracturing when subjected to vibration or impact. A simple connector that would shrug off a bump on Earth might shatter in lunar cold. Even the invisible helpers, the lubricants hidden inside motors, bearings and joints, are not spared. Oils thicken, then congeal, then in extreme cases nearly freeze, trapping parts in place. A mechanism designed to rotate freely can find itself locked not by damage, but by a change in the behavior of its own lubricant. In vacuum, conventional oils can also evaporate or break down, leaving surfaces bare and vulnerable to wear or welding together at contact points. The Apollo missions caught just a glimpse of these challenges. Astronauts stepping from the light into the cold shadow of the lunar module or into the shade of a boulder reported that equipment sometimes behaved oddly. Latches felt stiffer, cables changed tension. Certain components performed perfectly in the sunlit regolith, but grew reluctant when exposed to even brief drops in temperature. These were short visits, hours to a few days, yet they hinted at a world where, given weeks of darkness, the same systems might not simply become inconvenient. They might fail. Future lunar bases will not be weekend excursions. They will be months, then years of repeated thermal shocks. Habitats expanding and contracting, power systems cooling and reheating, vehicles parked in shadow and then driven back into searing light. The moon becomes not only a destination, but a test rig, a vast, unforgiving laboratory for the science of materials. To survive here, we must invent. Scientists and engineers are already exploring alloys designed to retain toughness at cryogenic temperatures, metals that do not surrender their ductility when the thermometer plummets. They are experimenting with ceramics and composite materials that can endure extreme heat on one side and deep cold on the other, holding a fragile, human-safe middle ground between them. New kinds of seals, metallic, flexible, or layered, attempt to replace ordinary rubber. Lubricants are being formulated that do not freeze or evaporate, that glide smoothly in vacuum at temperatures where water would be rock hard. Some of these solutions come from unexpected places. Technologies developed for deep space probes, which must endure the cold of the outer solar system, now find new purpose in lunar night. Advances from particle physics, where instruments sit in cryogenic baths, inform the design of future moon-based telescopes and sensors. Even quantum computing, which relies on components chilled close to absolute zero, pushes material science into regimes not unlike those on the lunar surface at midnight. Yet for all our ingenuity, one hurdle remains: testing. Simulating the moon on Earth is harder than it might seem. We can build vacuum chambers, cool materials with liquid nitrogen, and shine intense lamps to mimic sunlight. But replicating the exact combination of vacuum, radiation, extreme temperature swings, lunar dust, and months-long cycles of day and night is elusive. Most tests are compromises, slices of the real environment, not perfect copies. A metal joint may perform flawlessly through a few hundred accelerated thermal cycles in a laboratory, yet behave differently after years of subtle stress on the moon. A new polymer that seems robust under controlled conditions may absorb radiation in unexpected ways, turning brittle over time. The absence of air changes how heat flows, how surfaces cool, how cracks grow. We are learning, but the final exam will always be on the lunar surface itself. In this sense, every early outpost, every rover, every experimental habitat is more than a mission. It is a material science experiment written across an alien landscape. Each failed hinge, each cracked seal, each unexpectedly resilient component teaches us something about how matter behaves when stripped of Earth's gentle protections. The moon asks a simple, unforgiving question. What does it take for our tools, our shelters, our technologies to remain themselves when the world around them swings from fire to ice? To answer, we must learn to build not just for strength or efficiency, but for endurance in a place where even metal can forget it is metal and begin to act like glass. On Earth, dust is a minor nuisance. It settles on our bookshelves, gathers under our beds, and disappears with a swipe of a cloth. On the moon, dust is something else entirely. It is not a background detail of the environment. It is the environment. Every step, every landing, every breath taken inside a lunar habitat must contend with it. Here, dust is not soft, rounded, and harmless. It is sharp, ancient, and quietly hostile. Lunar regolith, the blanket of broken rock and glass that covers the moon, has never known rain, wind, or running water. On Earth, grains of sand are tumbled by oceans and rivers, smoothed into gentle curves by time. On the Moon, there is nothing to soften the edges. Each grain is fractured by countless micrometeorite impacts, splintered into jagged shards under the unfiltered violence of space. Many particles resemble tiny shards of broken glass mixed with powdered rock, each edge a microscopic blade. This alien soil does not merely lie still. Bathed in unending sunlight for nearly 2 weeks, then plunged into a darkness just as long, it responds to the Moon's changing electric environment in ways that are still not fully understood. The regolith is not just physical, it is electrical. Exposed to a constant stream of solar ultraviolet radiation and charged particles from the solar wind, it accumulates electric charge. Individual grains can grip to surfaces with a stubborn, almost magnetic tenacity, clinging to visors, spacesuits, seals, and instruments. During the transition between lunar day and night, something even stranger happens. The boundary between light and shadow on the Moon, known as the terminator, is not just a line of darkness creeping across the surface. It is a zone where the balance of electric charges suddenly shifts. Some models and observations suggest that, as the sun rises or sets, electric fields can form that are strong enough to lift tiny dust grains off the ground, making them levitate and drift in thin, ghostly layers above the surface. Apollo astronauts glimpsed hints of this phenomenon. Before sunrise at their landing sites, some reported a faint glow just above the horizon, as if a veil of dust was suspended in the airless sky, catching scattered light. The Moon has no atmosphere to hold dust aloft, no winds to carry it. And yet, for a brief time around the terminator, the regolith may become a slow, silent storm. Grains jumping, hopping, and gliding in arcs measured not in meters, but in electric potential. When the temperature drops with the coming night, this invisible storm changes character. The lunar surface plunges from blistering heat to deep cold, and the way dust behaves shifts with it. At extreme low temperatures, materials behave differently. Surfaces contract, trapped charges redistribute, contact points between grains tighten. The dust, already clingy, can become even more adhesive, locking itself into joints, radiators, and hinges with the stubbornness of frost in a lock. In this freezing environment, electrostatic forces do not disappear, they transform. The balance between charged surfaces, shadowed regions, and faint but persistent particle flux from space can cause dust to migrate in new patterns, creeping into areas that seem safely shielded in daylight. A radiator that shed dust under the warm glare of the sun may find itself quietly recoated as temperatures fall, its delicate thermal balance slowly compromised grain by grain. For the Apollo astronauts, the threat of lunar dust was not theoretical. It was immediate, physical, and inescapable. Their mission reports, written in calm technical language, read at times like accounts of a persistent, invasive life form. Dust found its way into every crevice of their spacecraft and suits. It abraded fabric, scuffed visors, and chewed into seals. It coated gloves so thoroughly that fine motions became difficult, like trying to work with hands dipped in sandpaper. Inside the lunar module, the dust did not stay outside like mud at a doorstep. It came in with them, clinging to suits, drifting off with every movement, filling the air with microscopic shards. Some astronauts reported a distinctive smell, like spent gunpowder, when the cabin was repressurized and dust began to interact with moisture and oxygen for the first time in eons. Their eyes itched. Their throats grew scratchy. They coughed. In those cramped, fragile habitats, the moon's soil became an unwelcome guest sharing their air. The longer we imagine staying on the moon, the more serious this becomes. A few days of exposure caused irritation. What might months or years do? Lunar dust is rich in tiny, sharp particles of silicate glass. On Earth, prolonged inhalation of certain silicate dusts can cause silicosis, a debilitating lung disease where scar tissue slowly chokes the ability to breathe. On the moon, dust particles, unweathered and angular, could be even more aggressive. Once lodged deep in human lungs, they would not dissolve. They would not smooth over. They would simply remain, tiny knives embedded in fragile tissue. This possibility is more than a medical concern. It is a design constraint on everything we send to the lunar surface. Habitats must become fortresses, not against storms or predators, but against powder. Airlocks need to function as decontamination chambers, stripping dust from suits and tools before they enter living spaces. Filters must be built to capture particles that are eager to travel through the smallest gaps. Over years, lunar exploration may become a careful negotiation with a pervasive toxic powder that waits patiently at every doorstep. Dust is just as dangerous to machines as it is to people. On the moon, temperature is a silent enemy, and we rely on carefully engineered surfaces, radiators, reflective coatings, multi-layer insulation to keep equipment within survivable limits. Thermal control systems are designed like tuned instruments, each surface with a calculated ability to absorb and radiate heat. Lunar dust, settling where it will, is a careless hand smearing dirt across the keys. A thin layer of dark dust on a reflective surface can absorb more sunlight and trap heat where it should be rejected. On the night side, that same layer can alter how quickly a surface loses heat to the blackness of space, making it cool faster or in unexpected ways. As dust accumulates on radiators, solar panels, and thermal blankets, the carefully plotted flow of energy into and out of a habitat begins to drift. Temperatures may start to swing beyond safe ranges. Electronics may run hotter. Batteries may chill too deeply. Systems designed with narrow safety margins could begin to fail, not with a dramatic event, but with a slow, dust-driven slide out of specification. This is the quiet power of lunar regolith. It does not roar like Jupiter's storms or blaze like the sun. It acts grain by grain, in silence. It follows the cycles of light and dark, waking into motion at the terminator, settling into shadow, weaving itself into the story of every joint, filter, and lung that dares to operate on the surface. In the eternal cold of lunar night, when the last rays of sunlight retreat and the temperature drops toward extremes that test the nature of matter itself, lunar dust does not sleep. It tightens its grip, hardens its presence, and deepens its reach into the machinery and biology that attempt to endure. It is the assassin that never lifts a weapon, only a particle, and waits for time and repetition to do the rest. To survive the moon is to learn the language of its soil, not just how to walk on it, but how to keep it out of the air we breathe, away from the circuits that guide us, off the surfaces that keep us warm. In the stillness of lunar night, while the world above lies buried in stars and shadow, the true struggle may be happening at the smallest scales, where a single grain of dust, sharpened by billions of years of silence, can become the first step toward failure or the first lesson in how to live with an alien world. The physical dangers of lunar night can be measured in watts, degrees, and millimeters of metal. The psychological dangers are measured in something far more elusive: the quiet shifting of the human mind when the sun disappears and does not return. On Earth, we already have a preview of what this means. Near the poles, winter brings not just cold, but a darkness that lasts for months. In places like northern Norway, Antarctica, and the high Arctic, the sun sinks below the horizon and refuses to rise. The world does not end. Trains still run, people still work, children still play. But beneath the routines, something subtle changes. Doctors see patterns: rising rates of depression, more frequent sleep disorders, a gentle but persistent erosion of focus and memory. People who feel perfectly fine in summer find themselves heavy and slowed in winter, as if their minds are wading through dim water. This is not simply a matter of mood. It is biology, responding to the absence of light. Our bodies are not built for endless night. Deep inside our brain, a tiny clock made of neurons pulses in a rhythm of roughly 24 hours. This circadian rhythm governs when we feel sleepy, when we wake, how our hormones rise and fall, how our temperature drifts through the day. It is tuned every morning by light from the sun. A sunrise is not just a beautiful sight. It is a daily reset signal, a cosmic "you are here" for the human nervous system. On the moon, that signal disappears for nearly half a month at a time. Imagine standing on the lunar surface as the last sliver of sun sinks behind the horizon. Shadows stretch, lengthen, and then merge into a single vast pool. Unlike Earth's twilight, there is no scattering atmosphere to smear light into delicate colors. Day becomes night like a switch being thrown. One moment, the ground blazes with harsh, unfiltered sunlight. The next, the world falls into an uncompromising black. Above you, the sky remains dark, but now it is absolute. A pitch-black dome pricked by brilliant, unblinking stars. Earth hangs there, luminous and distant, but the sun itself is gone, swallowed behind the slow-turning horizon. And it will not return for 14 Earth days. For the human brain, this is not just an absence of light, it is an absence of time. Without sunrise and sunset, our internal clocks begin to drift. Some people's rhythms naturally stretch longer than 24 hours. Others shorten. In terrestrial experiments, volunteers living in caves, cut off from daylight, gradually slide out of sync with conventional time. They begin going to sleep later each day or earlier until their internal day bears little resemblance to the one ticking on the surface above them. Now imagine this drift happening not in a controlled bunker in France or a lab in Colorado, but in a small habitat on the moon, far from home, with no easy way back. This is where isolation deepens the darkness. A lunar outpost will not be a bustling city. It will be more like a small ship in a vast, silent ocean. A handful of people, the same faces, the same voices, the same few rooms, day after day, while outside lies a landscape that is both stunning and utterly inhospitable. On Earth, even during polar night, most people know that if things become unbearable, they can, in principle, leave. A plane can be boarded, a train can be taken. The knowledge of an exit, even if unused, offers a kind of psychological safety net. On the moon, that net is mostly theoretical. The next launch window may be weeks away. The systems that keep you alive cannot simply be walked away from. The darkness is not just outside. It is part of the architecture of your situation. History offers us analogues, fragile mirrors held up to the future. Early Antarctic expeditions spent winters in cramped huts buried in snow, with oil lamps for light and storms howling outside. Their journals describe boredom deepening into irritability, small annoyances swelling into obsessions, the sense of time stretching and looping until days felt indistinguishable. They gave names to it: winter madness, the polar bug. Not everyone succumbed, but no one was untouched. Submariners know a different version: weeks or months underwater, no windows, only artificial light, strict routines. The outside world becomes an abstraction, reduced to updates over radio. Within the steel hull, life is carefully timed, every hour scripted. Sleep schedules, meal times, work rotations. Each piece is a tool to hold the mind in a stable orbit when there is no sunrise to do the job for them. On the Moon, during its long night, astronauts will exist in a kind of hybrid of these experiences. Antarctic remoteness, submarine confinement, polar darkness, all at once. This is why artificial light is not a luxury in a lunar habitat. It is medicine. To preserve mental health, the habitat's light will need to do more than simply turn on and off. It will need to mimic dawns and dusks, the warm rise of morning light, the cooler hues of afternoon, the gentle dimming toward evening. Lamps tuned to specific wavelengths can help regulate melatonin, the hormone that signals sleep, and cortisol, which nudges us awake. Light will become a carefully prescribed substance, dosed in hours and lux instead of milligrams. Just as important as the light itself is the pattern it follows: a clear, consistent schedule, set wake times, meals, work periods, exercise and rest, acts as scaffolding for the mind. Each recurring event says quietly, time is still moving, and you are moving with it. Without this scaffolding, days can blur, and with them, motivation and mood. There is a paradox here. The environment of lunar night is unlike anything humans have lived in, yet the tools to survive it are rooted in some of the simplest human experiences: regularity, routine, and rhythm. Researchers studying Antarctic bases have found that crews who embrace structure, in work, in shared meals, in recreation, fare better than those who let time become amorphous. Even small rituals, like a weekly movie night or a shared meal to mark the end of the week, help create landmarks in otherwise featureless stretches of time. In submarines, similar traditions emerge. Certain days for certain foods, recurring games, shared jokes. They become a calendar of the heart when the outside world offers no calendar of its own. On the Moon, during the 2-week night, such rituals may be as vital as any piece of life support hardware. The knowledge that every lunar night Tuesday you will call home, or every night 10 you will all gather for a particular activity, offers something for the mind to orbit around. Yet even with all of this, some questions remain open. How will the combination of low gravity, prolonged darkness, and truly remote isolation shape the human psyche over months or years? Will some individuals find the experience uniquely peaceful, a kind of monastic retreat in space? Will others find their thoughts turning inward in ways we do not yet fully understand? Psychology in space is still a young science. We can extrapolate from Antarctica, from submarines, from polar towns ringed by winter darkness. These are valuable guides, but not perfect maps. There will be surprises, both challenging and inspiring. What is clear is that surviving lunar night is not only about keeping air breathable and water liquid. It is about keeping minds anchored. The endless night outside will test more than our machines. It will test our ability to carry daylight within us, to generate our own cycles of meaning and rest, wakefulness and wonder, when the sky above offers only stars and silence. In this way, the psychological darkness of lunar night becomes more than a threat. It becomes a question. How well do we understand the rhythms that make us human? And can we recreate them, faithfully enough, 250,000 miles from home? The moon is a world of extremes, but hidden within those extremes are rare places that almost seem to bend the rules. After wandering through the long frozen night, we arrive at a kind of sanctuary written quietly into the moon's geometry. The peaks of eternal light. The phrase sounds poetic, almost mythical, as if lifted from an ancient legend. Yet it is a technical term, born not from fantasy, but from the cold, precise dance of angles, shadows, and sunlight at the lunar poles. On most of the moon, the rhythm is brutal and simple. 2 weeks of relentless day, 2 weeks of unbroken night. Temperatures surge, then collapse. Power systems feast on sunlight, then starve in darkness. But near the poles, something different happens. Here, the sun never climbs high into the sky. It hovers low on the horizon, circling slowly, skimming along the edge of sight like a lantern carried around the rim of a distant bowl. Because the moon's axis is tilted only about 1.5 degrees relative to its orbit around the sun, far less than Earth's generous 23.5 degrees, its poles never lean dramatically toward or away from the light. The result is a strange compromise between day and night, written into the very tilt of the world. At the lunar poles, valleys can be plunged into darkness for billions of years, while nearby mountain ridges and crater rims touch the light over and over, orbit after orbit. Here, the drama of sunrise and sunset flattens into a kind of subdued, perpetual twilight. Where the terrain rises high enough, the peaks sit above the deep shadows, catching sunlight whenever the sun grazes the horizon. These are the peaks of eternal light, regions that remain illuminated for most of the lunar year, missing only brief intervals when the sun dips behind distant terrain. They are not truly eternal. No place on the moon is lit 100% of the time. Yet some polar ridges approach a kind of practical eternity. Certain points near the South Pole may see sunlight 80%, 90% or more of the year. To engineers trying to keep instruments warm and batteries charged through the unforgiving lunar cycle, that difference is not cosmetic. It is the difference between trying to survive in a hostile desert and settling on the edge of a gentle, if fragile, oasis. One of the most intriguing of these oases is a region often referred to as the Connecting Ridge, perched near the lunar South Pole. It is not a vast plateau or sprawling plain. It is a narrow, elevated stretch, a slender bridge of higher ground that stands above the surrounding landscape. Simulations and illumination studies suggest that parts of this ridge could be bathed in light for the vast majority of the lunar year, interrupted only by short, predictable eclipses of darkness as the sun briefly slips behind nearby peaks or crater walls. For mission planners, this is more than an interesting curiosity. It is a lifeline. On ordinary lunar terrain, designing a base means confronting 2 weeks of deep cold, no solar power, no easy way to keep machinery, habitats, and human bodies within survivable limits without enormous reserves of energy. But on a peak of near eternal light, solar panels can sip power almost constantly. Thermal swings are gentler. Batteries can be smaller. Life support systems can be simpler. The hostile rhythm of day and night is softened into a more manageable pulse of dimming and brightening, rather than oblivion and glare. And yet, nature's loophole comes with conditions. These peaks are tiny in area, perhaps no larger than a handful of city blocks, sometimes just narrow ridgelines barely wide enough for a modest outpost. Their surfaces are rugged, sloping, and cluttered with rocks and slopes that complicate landing and construction. A spacecraft must thread a careful path, aiming for an elevated spine of terrain where even a small error could mean a descent into more ordinary, less forgiving polar ground. There are other challenges. The same low sun that grants long-lasting light also casts long shadows, carving sharp contrasts into the landscape. Navigation can be tricky. Temperatures are still cold, especially compared to equatorial regions, and dust remains ever present, ready to coat solar panels and mechanical joints. The peak's advantages are significant, but they are not a magic escape from the moon's underlying hostility. They are more like a slightly milder climate in a world that never truly becomes gentle. What makes these locations even more remarkable is what lies just below them. Wrapped around the poles are craters so deep and so steep-walled that sunlight never touches their floors. These are the permanently shadowed regions, ancient cold traps where temperatures plunge so low that water molecules drifting across the lunar surface can freeze and accumulate over millions, even billions of years. Radar and spectral measurements suggest that some of these craters may harbour significant deposits of water ice mixed into the regolith. This pairing, a sunlit ridge beside a crater of eternal night, is one of the most extraordinary juxtapositions in our solar system. On a connecting ridge, a base could gather nearly constant solar energy on its panels, while a short rover journey away, in the darkness of a nearby crater, explorers might dig into ice that could be turned into drinking water, breathable oxygen and rocket fuel, light and ice, energy and resources, survival and expansion, all nested within a few tens of kilometers, sculpted not by human design, but by the quiet logic of orbital mechanics and geology. It is no accident that almost every major spacefaring nation has now turned its gaze toward the lunar South Pole. NASA's Artemis missions, robotic landers from multiple countries, commercial ventures, and long-term base concepts all converge on this same region. The South Pole is not just a point on a map. It is a strategic crossroads where the moon's most valuable natural advantages intersect. Peaks of near-eternal light offer power and thermal stability. Shadowed craters promise ice, perhaps vast reserves locked away in perpetual cold. In this narrow band between darkness and dawn, the dream of a sustainable lunar presence becomes less abstract. If humanity is to build not just brief camps but lasting footholds in the lunar environment, the South Polar Highlands offer our best chance to do so without hauling every drop of water and every watt of energy from Earth. The geometry of the moon, set billions of years ago, now quietly favours our ambitions. These peaks, these ridges, these knife-edged horizons of almost unbroken sunlight remind us that even in harsh environments, nature sometimes leaves small openings, not safe harbours, but less hostile ledges where life and technology can clutch, stabilise, and grow. The peaks of eternal light do not erase the danger of lunar night. They do something subtler. They give us leverage, a place to anchor our efforts, a margin of safety in a world that usually offers none. As we imagine future astronauts standing on those illuminated ridges, watching the sun skim endlessly along the horizon, while the craters below remain locked in timeless shadow, we see a new chapter of exploration taking shape. From these narrow zones of almost continuous day, humanity may one day look back across the gulf of space, knowing that our path into the deeper solar system began not with conquering the darkness, but by carefully, patiently, stepping into the light that never quite fades. Engineering survival on the moon begins with an uncomfortable truth. Nothing there wants us to last. The cold is not just low temperature. It is the absence of heat itself. The night is not just darkness. It is the turning off of almost every natural source of energy we depend on. And yet, piece by piece, engineers are beginning to sketch out ways to bend this hostile environment, not through brute force, but by learning to store, redirect, and recycle every fragment of warmth and power the lunar day provides. One of the most intriguing ideas is something that sounds almost poetic: thermal wadis. On Earth, a wadi is a dry riverbed that only flows after rare rains. On the Moon, the rain is sunlight, and the river is heat. The concept is simple in spirit, but subtle in execution. During the lunar day, vast blocks of regolith, the dusty rock that covers the Moon, would be reshaped, darkened, and layered with materials designed to drink in sunlight. Like a desert rock that still radiates warmth long after sunset, these engineered mounds would slowly release their stored heat back into their surroundings during the 2-week night. In a way, a thermal wadi is an artificial oasis of temperature in a landscape that wants to plunge to hundreds of degrees below freezing. Habitats, greenhouses, or storage modules could be nestled near or within these heat reservoirs, tapping into their steady, declining warmth through heat exchangers and insulated piping. The wadi does not eliminate the cold. It stretches the descent into it, buying precious days before other systems must take over. On the Moon, time itself becomes a resource, and thermal wadis are designed to store hours as much as degrees. Still, even the best surface system must confront the fact that the lunar environment swings like a pendulum from blazing sunlight to starless chill. A more ancient, quieter solution lies beneath. The Moon's crust is riddled with lava tubes and caves, hollow channels carved billions of years ago by flowing magma. These subsurface spaces are not cozy, but they are consistent. While the surface gasps through wild temperature cycles, the interior rock changes slowly, buffered by its own mass. Here, the temperature is less a storm and more a seasonal drift. Underground habitats propose to use this calm as a shield. Instead of building domes that stand exposed on the surface, we might carve into crater walls or seal off sections of lava tubes, using meters of rock and regolith as natural insulation against both heat and cold. Buried modules could be surrounded by compacted lunar soil, turning the very material that once threatened our machines into a protective blanket. Inside, life support systems would no longer have to fight the full violence of the night. They would only have to manage a softened, filtered version of it. Yet rock alone cannot hold the line forever. To bridge the long lunar night, engineers also look to materials that transform quietly as temperatures shift. Phase change materials are substances that absorb or release large amounts of heat when they change state, from solid to liquid or liquid to solid, at specific temperatures. On Earth, paraffin wax in some building walls melts as a room warms, soaking up excess heat, then solidifies as it cools, returning that energy back. On the Moon, more extreme versions of this idea are being explored. Salts, metals, and engineered compounds could be tuned so that their melting point aligns with the comfortable operating range of a habitat or battery bay. During the lunar day, they would melt, loading themselves with thermal energy without getting much hotter. During the night, as the environment cools, they would slowly solidify, releasing that stored heat in a controlled, predictable way. Instead of heaters flicking on and off, you would have thermal tides, rising and falling as atoms reorganize themselves in silence. But heat is only half the equation. The other half is power. With no sunlight for 2 weeks, solar panels become frozen mirrors, useless until dawn. Here, another elegant strategy emerges: regenerative fuel cells. At first glance, They are cousins of the systems that once kept Apollo astronauts alive. During the day, excess solar power is used to split water into hydrogen and oxygen. These gases are stored, separated and pressurized, waiting. When the night falls and the panels go dark, the process reverses. Hydrogen and oxygen are recombined in fuel cells, generating electricity and producing water again as a byproduct. In essence, the lunar base breathes. By day, it inhales sunlight and exhales stored chemical energy. By night, it inhales hydrogen and oxygen and exhales electricity and water. Nothing is wasted if it can be cycled. The challenge is scale. To survive a full lunar night, the tanks, pipes and cells must be sized not for hours, but for hundreds of hours. Every leak, every frozen valve, every misplaced seal becomes not just an inconvenience, but a countdown. Guarding all of this, thermal waddies, underground rooms, whispering fuel cells, are the quiet, unsung layers of protection that stand between delicate human equipment and the relentless vacuum. Multi-layer insulation systems are like high-tech blankets, made not of fabric, but of thin reflective foils and spacers stacked dozens of times over. Between each layer, emptiness. No air to conduct heat, no water to freeze, only space for radiation to bounce, reflect and weaken. These blankets do not keep the cold out the way a winter coat does. Instead, they slow the exchange of heat between the habitat and its surroundings until time itself blurs. Inside, warm surfaces radiate outward. Outside, the cosmic background and lunar night pull that warmth away. Each layer of foil turns that journey into a maze, forcing thermal radiation to ricochet, hesitate, diminish. Combined with buried walls and phase change cores, multi-layer insulation becomes part of a choreography designed to make temperature change feel less like a cliff and more like a slope. Underneath all of these ideas lies one final principle, less visible than wires or pipes, but even more essential: redundancy. On the moon, failure is not a single event. It is a chain. A pump stalls, a valve sticks, a wire cracks in the cold. The danger arrives when all these small failures line up. To break that chain before it tightens, lunar engineering follows a philosophy that can seem almost obsessive from Earth. Every critical system must have not just a backup, but a different kind of backup. If solar power fails, nuclear heat or fuel cells must be ready. If a thermal waddy underperforms, phase change materials and buried habitats must take up the slack. If a heater burns out, passive insulation must be thick enough to buy hours or days for repair. Power lines are duplicated. Sensors are triplicated. Even the paths by which heat flows are diversified, so that a single frozen pipe cannot isolate an entire module. This layered approach does more than protect machines. It protects time. Redundancy stretches the moments between problem and crisis, between first warning and irreversible loss. In the endless night, where rescue is weeks or months away, time is the most precious commodity of all. Our survival on the moon will not depend on a single perfect invention, but on a web of imperfect ones, overlapping, compensating and enduring together. In these strategies, thermal waddies that hoard daylight, caves that cradle warmth, materials that change state like slow-motion tides, fuel cells that turn light into stored breath, and blankets of metal that confuse the cold, we see the outline of a possible future. Not a triumphant conquest of the lunar night, but a quiet truce with it, a recognition that to live there, we must think like the moon itself, patient, deliberate, and always preparing for the next long darkness. To understand the danger of lunar night, we do something unexpected. we turn away from the moon and look back at Earth. Not to the warm blue oceans or the glitter of cities at dusk, but to the white silence at the bottom of the world. Antarctica is the closest thing our planet has to an alien realm, a continent of ice, sealed beneath a sky that can stay dark for months, with air so cold it steals heat like a thief. Here, in this frozen isolation, we find our first real rehearsal for surviving the moon. On the high, wind-scoured plateau of East Antarctica stands Concordia Station. To some, it is simply a research base. To others, it is White Mars. Concordia spends the austral winter in almost continuous night. For nearly 6 months, the sun does not rise. Temperatures plunge below -80 degrees Celsius. The air is thin, the humidity vanishingly low, and the outside world is lethally cold. Step outside without protection, and exposed skin can freeze in seconds. Inside, a handful of people live in a metal outpost surrounded by infinite darkness. They work, they eat, they sleep, they wait. Resupply is impossible. Evacuation is impossible. Once winter sets in, no aircraft can safely land. Whatever breaks must be fixed with what they already have. Whoever gets sick must be treated with the skills on board. For months, the crew watches the same corridors, the same faces, the same artificial lights. Circadian rhythms drift. The difference between 3 a.m. and 3 p.m. is no longer written in the sky, only in the clock, and in the quiet fatigue behind people's eyes. It is not just the cold that makes Concordia an analogue for the moon. It is the combination of factors: extreme environment, isolation, confinement, and the knowledge that outside is not a place of refuge, but of danger. Here we study not just ice cores and distant galaxies, but the human mind and body under conditions that echo a lunar night. Researchers track sleep patterns as the months of darkness progress. Insomnia creeps in for some, oversleeping for others. Melatonin cycles flatten. People report strange dreams, dips in mood, waves of anxiety and detachment. Even conversation changes. Voices grow quieter. Small frictions can echo for days. From Concordia, we learn how crucial light is, not just for visibility, but for sanity. Carefully timed lamps mimic sunrise and sunset. Color temperature becomes medicine. A soft blue-white in the morning, a warmer amber in the evening, artificially sculpting a day in a world where the sun has vanished. We also learn how vital routine becomes. In an environment where nothing outside changes, the only seasons are the ones you create. Exercise, shared meals, weekly rituals, small celebrations. These are not luxuries. They are structural supports for the mind. Yet even Concordia sits under a blanket of atmosphere that Earth kindly provides. Step outside, and you still breathe air, however cold. On the moon, there is no such mercy. A punctured suit is not frostbite. It is vacuum. From the polar plateau, we turn now to another hidden environment, the silent corridors of a submarine, deep beneath the ocean's surface. Submariners live for months without natural light. Steel walls press in. Space is limited. Privacy is almost non-existent. The outside world is not a landscape, but a pressure that could crush the hull in an instant. Life here is governed by the clock, not the sun. Days blur into watch cycles. Hours on duty, hours off, repeated again and again. Artificial lights never truly mimic dawn or dusk. They simply signal when to work, when to rest, when to eat. In this submerged world, every breath you take has been engineered. Air is scrubbed of carbon dioxide, filtered of contaminants, carefully recycled. Water is distilled. Waste is processed. The environment inside the submarine is a living system, constantly maintained. Failure is not a technical inconvenience. It is an existential threat. From submarines, we learn the art of invisible life support, the importance of redundancy, multiple backups for any system that keeps humans alive, the necessity of quiet, constant maintenance, long before alarms begin to sound, and the subtle impact of confinement on mood, cooperation, and performance. Antarctic stations and submarines together form a kind of mirror for future lunar bases. They teach us that survival in extreme isolation is not a matter of technology alone, but of daily habits, culture, and careful design of the human environment. Yet there are differences, sharp, uncompromising ones. On Earth, even at Concordia, even in a submarine, there is still a margin. In a crisis, someone can step outside. A rescue, while difficult, is at least possible given enough time and luck. On the Moon, especially during lunar night, that margin almost disappears. In an Antarctic winter, a mechanic can bundle up and trudge across ice to repair an external antenna. On a submarine, an engineer can access most systems without a suit or an airlock. On the Moon, every step beyond the habitat wall is a spacewalk. Every repair must be done in a pressurized suit, in bone-deep cold, in darkness lit only by artificial lamps or distant starlight. If a cable freezes and snaps, if a radiator line cracks, if a valve seizes outside the shelter during the 2-week night, you cannot simply rush out and take a quick look. Each intervention is a high-risk operation. This changes how we think. Systems must be designed to survive the entire lunar night without human touch. Components must be reachable from inside, or built with such resilience that they can sleep through the cold and wake up intact. Where Antarctica teaches us how to endure isolation, the Moon demands something more: the ability to endure isolation from our own infrastructure. To prepare for that, we do one more thing on Earth. We build the Moon in miniature, inside domes, on deserts, beneath mountains. We call them analog missions. In places like NASA's Hera habitat, crews spend weeks in a sealed environment, simulating deep space journeys, asteroid visits, and planetary stays. They practice communications with built-in delays, strained by the absence of real-time reassurance. They simulate emergencies and measure how quickly stress-phrase teamwork. On the slopes of Mauna Loa in Hawaii, HICS missions place small crews inside a dome that imitates a Martian or lunar base. The outside landscape is volcanic and barren, a rough cousin to alien basalt. For months, participants live as though they are truly off-world. They go outside only in suits. They manage limited resources. They learn how minor annoyances between people can grow in a closed loop of conversations and routine. Other simulations dot deserts, Arctic islands, even underwater habitats. Each one removes one layer of comfort: spontaneous walks, instant messages, the unthinking abundance of Earth. What remains is the core puzzle. How do humans live and stay human when the world outside the wall is hostile to life? From these analogues, we learn surprising lessons. That the design of a common room can influence mood as strongly as a medical intervention. That a small window with a view, even of a simulated landscape, can reduce stress. That giving people meaningful work, a sense of purpose, can act as insulation against isolation. Antarctica, submarines, sealed habitats on lonely mountains. These are our laboratories of survival. They do not let us feel the vacuum or the harsh chill of lunar regolith at night, but they let us feel the weight of time, the press of confinement, the subtle erosion of sleep and patience. They show us that surviving the lunar night is not simply about not freezing. It is about not fading. Technically, psychologically, socially. Standing on the moon, at the edge of the long darkness, we carry these lessons with us from Earth's most extreme corners. They are our rehearsal. But the main performance is still to come. NASA's Artemis program is the first deliberate step into that unknown. Its goals are written not in terms of single missions, but in terms of years, infrastructure, and continuity. Artemis 1 has already traced a distant loop around the moon, testing the spacecraft that will carry humans farther than any have traveled before. Artemis 2 will bring astronauts back into lunar orbit. Artemis 3 and beyond aim to land humans near the South Pole, where sunlight grazes crater rims and water ice may wait in the shadows. Yet the true ambition of Artemis is not the first landing. It is the idea of sustained lunar presence. That phrase sounds simple, but hidden inside it is a quiet revolution. To sustain is to endure the lunar night, to accept that we cannot simply time our visits with the sunrise and hurry home when the shadows grow. We must learn to live through the long darkness that once made the moon seem uninhabitable. The Artemis Base Camp and related concepts imagine power systems, habitats, and logistics chains that do not shut down when the sun sets for 2 Earth weeks. The timeline may shift, as all ambitious plans do, but the direction is now clear. The moon is no longer an endpoint, it is a frontier. We are not going alone. Orbiting high above the grey surface, a new kind of outpost is being planned, the Lunar Gateway. Unlike the International Space Station, which circles Earth in a constant bath of sunlight and planetary protection, Gateway will swing in a wide, halo-like orbit around the moon. It will drift in and out of the lunar night, a small, distant lighthouse for crews travelling between Earth and the surface. Gateway is an experiment not only in engineering, but in collaboration. Built through partnerships between NASA, the European Space Agency, Canada, Japan, and others, it represents a recognition that no single nation needs to own the moon in order to explore it. European modules, Canadian robotics, Japanese logistics, American propulsion, each piece contributes to a shared foothold in cislunar space. Future missions from other countries, like China's growing Chang'e program or emerging efforts from India, South Korea and beyond, may build parallel infrastructures, cooperating, competing, or quietly learning from one another. The result could be a web of stations, relays and depots that turn the once isolated lunar night into a region threaded with human-made constellations. Beneath this layer of national flags and international agreements, another force is reshaping what is possible: the private sector. Companies like SpaceX and Blue Origin are changing how we think about cost, frequency, and risk. Reusable rockets, once the domain of science fiction, now land themselves with practiced grace. Where a single Saturn V launch once consumed enormous national resources, a future Starship or New Glenn flight could become one of many regular departures, lifting cargo and crew with a rhythm more like shipping lanes than singular events. This shift matters profoundly for the lunar night. Surviving in that darkness is not a one-time stunt. It is a supply chain problem, an energy budget problem, a manufacturing problem. Lower launch costs and higher flight rates mean more room to experiment. Multiple designs for power stations, buried habitats, or thermal storage systems can be tested, iterated, and replaced. Smaller firms can attempt bolder ideas: wireless power beaming, cryogenic storage farms in permanently shadowed craters, or modular reactors designed to shut down and restart across countless nights. The economics of space are beginning to bend, and with that bend, some of the harshness of lunar night becomes less absolute. Before humans attempt to sleep through that darkness in a habitat windowed against the stars, machines will go first. Robotic precursors are already tasting the edges of lunar night, and more are being designed to venture deeper. Landers equipped with experimental batteries, fuel cells, or miniature nuclear heaters are sent to see whether electronics can endure weeks of brutal cold cycles. Tiny rovers may huddle in shadow, drawing on stored heat, waiting to wake with the returning dawn. Some will fail. They will freeze, crack, fall silent. Their loss will not be in vain. Each failure maps another boundary of what materials can endure, what designs need revision, what assumptions were too optimistic. Others will surprise us, surviving longer than expected, waking after thought to be fatal nights with data still streaming. In these quiet experiments, scattered across craters and plains, we are rehearsing the choreography of human survival. We are teaching ourselves how to build homes for the dark. Beyond these first steps lies a more distant, shimmering vision. The moon as a place where we make things, not just visit. Lunar regolith melted into glass and ceramics. Metals extracted from ancient basalt flows. Dust compressed into bricks, habitats, and radiation shields. Over time, a base that once depended on Earth for every bolt, wire, and panel could begin to manufacture its own replacements. Power cables, spare parts, even greenhouses might one day be built on site, turning the long lunar night into a cycle that industry simply plans around, the way farmers on Earth once planned around winter. In some scenarios, the moon is imagined as a reservoir of exotic resources. One such dream centers on helium-3, a light isotope deposited by the solar wind and preserved in the lunar soil. Some have proposed that helium-3 could fuel future fusion reactors, offering clean energy on a planetary scale. Whether this vision will ever be realized remains deeply uncertain. Fusion itself is still under development, and the practicality of mining and transporting helium-3 is unknown. Yet the concept is a reminder of how the moon constantly challenges our imagination. A cold, airless body becomes, in theory, a key to energy for an entire civilization. Perhaps the most profound role of the moon is not as a warehouse, but as a classroom, a stepping stone. Before we attempt to cross the Gulf to Mars, where nights can be bitterly cold, dust storms can blot out the sun for weeks, and resupply is measured in years rather than days, we will practice in our own cosmic backyard. Habitats that endure the lunar night will inform Martian bases. Power systems that bridge 14 days of darkness will inspire designs for worlds where sunlight is weak and intermittent. Medical, psychological, and social lessons learned under the slow cycle of lunar day and night will echo in the domes and tunnels of future Martian settlements. Yet for all these plans, timelines, and technologies, a veil of uncertainty remains. The lunar night may reveal new materials that behave in ways we do not yet anticipate. Ice deposits we hope to exploit may be patchier, deeper, or more fragile than expected. Dust might cling in surprising ways. Electronics may age under radiation differently than our models predict. And human minds might respond to the rhythm of 2-week days and 2-week nights with patterns we have yet to understand. We may also discover solutions we have not yet dreamed of. Novel energy storage methods, unexpected synergies between systems, or simple design insights that turn a severe problem into a manageable inconvenience. The history of exploration is filled with both unforeseen dangers and unexpected elegance. In the end, the future of lunar night is not a fixed destiny, but a question we are slowly learning to answer. It invites us to think beyond the comfort of sunshine, beyond the short cycles of earthly days, to imagine a human presence that can endure in silence and shadow, in cold and time, and still awaken with each distant dawn, ready to continue the story we began when we first looked up and wondered what it would mean to call another world home. In just 66 years, humanity went from the first powered flight at Kitty Hawk to bootprints in lunar dust. A single lifetime carried us from canvas wings trembling over a beach to a Saturn V shaking the sky. In cosmic terms, that span of time is less than a heartbeat. Yet in that heartbeat, we learned to leave the planet that made us. Now, the moon is inviting us to attempt something even harder. Surviving its long, airless night is not just a technical obstacle. It is a new chapter in the story that began when someone first looked up and wondered what that pale light really was. The lunar day was our first visit. The lunar night will be our true arrival, when we find ways to endure 2 weeks of killing cold, of power lost and regained, of machines and minds stretched to their limits. We will not only be building bases on the moon, we will be rehearsing for every distant place that waits in the dark. The frozen shadows of Mars' poles, the night side of Mercury, the caves of icy moons where sunlight never reaches, but oceans might breathe beneath the surface. Each challenge we solve on the moon becomes a tool we can carry with us into deeper space. Heat stored through long darkness, power systems that never truly sleep, materials that do not crack when atoms slow and metals turn brittle, life support that can comfort a human mind that has not seen a sunrise in days or weeks or months. The lunar night is not a dead end. It is a training ground. Some future explorer stepping out onto the surface of Europa or into the shadow of a crater on an asteroid may owe their safety to lessons we first learned on the moon's cold side. When their habitat stays warm, when their power does not fail, when their spirits remain steady in the silence. All of it will trace back to this nearby world that has watched over Earth since before there were eyes to see it. Tonight, if you look out a window, the moon you see hanging quietly above roofs and treetops is not just a familiar ornament in the sky. Beneath that serene light lie temperatures that swing hundreds of degrees, dust as sharp as glass, and a night so long that every heartbeat of warmth must be planned in advance. That calm circle of light is a puzzle still unsolved, a mystery still in progress. Yet it is close. Close enough that its gravity tugs at our oceans. Close enough that signals from future lunar bases will reach Earth in just a little more than a second. The same moon that inspires poems and lullabies is also our first true frontier. Close enough to touch with radio waves, harsh enough to reshape our technology and our imagination. Thank you for drifting through this journey into lunar science and into the quiet danger of the moon's endless night. If you've enjoyed exploring these ideas in a calm, unhurried way, you can gently tap like or subscribe to join us for future voyages through space and time. I'd love to know where in the world you're listening from. If you feel comfortable, leave a comment sharing your city, your country, or simply the kind of sky you see when you look up. For those who wish to support the channel a little more, there is an optional YouTube membership, a way to help keep these slow, thoughtful explorations adrift in the algorithmic currents. It is never required. Your presence here, your curiosity, is already part of the story we are telling together. As you rest, remember, above you, the moon is turning, passing through day and into a night that would freeze unprotected metal and silence careless machines. One day, perhaps sooner than we expect, humans will watch that nightfall from the surface, not as visitors racing against time, but as residents prepared to endure. Between their first sunrise and their first lunar midnight lies humanity's next great adventure, waiting, quietly, in the dark.